I'm Steve Swartz. I'm an architect on the Connected Systems Division at Microsoft. And this is Clemens, the program manager working specifically on the programming infrastructure, the program frameworks. And we are here giving you 6 talks. Yesterday was the first 2 today, 2 tomorrow. The first talk tried to tell the story of all the products Microsoft is selling in the connected space. Everything between the database over here and ASP.NET over here, all the stuff in the middle that you're using to build connected applications. We sort of gave you that picture so you'd know where everything sat. And now we're going through a set of 4 architectural talks where we're trying to establish the big ideas that our division is using to organize the product thinking we're going to do over the next few years. So you can see these talks, and first off, it's our notion of sort of the architectural meta principles, the big ideas in these spaces. And second, it gives you a sniff of the future. If you start thinking this way, you know you'll be thinking in a way that we're thinking, and that is, of course, useful. This talk is about data. The talk early this afternoon will be about presentation, about rich clients, smart clients. And then tomorrow we're going to talk about security and the future. I'm going to try to keep my job talking about the future, even though I'm not allowed to talk about the future.
You talk about looking forward.
Looking forward, there you go. So when I'm talking about data, I'm not trying to be talking about database design, index optimization, all that kind of stuff. SQL has got a beautiful, rich world, and I'm not trying to look inside of it. I'm trying to step back and think about data from the point of view of how it is to think about data as part of a system-oriented or service-oriented connected application. And so we're going to be thinking about how to deal with data in the large, not inside the database, but from the point of view of your whole app. And we're going to talk about 3 things. I'm going to start by talking about the big characteristics of data. One of the points I want to make here is that yesterday when we talked about the basic patterns in connected logic, those patterns actually kind of arise out of fact, and you end up finding those patterns in your application. Whereas my argument is going to be that the characteristics of data are, in fact, decisions you make and impose on the world. Data is very gushy stuff. We like to call it specific things, read only or read write, when in fact those are assumptions that your app makes. After that, we're going to go through and talk about some patterns. Those are patterns and strategies you can use to deal with data in a connected app. And then as before, and as we're going to do the rest of the time, rather than looking at a specific demo, we're going to look at a variety of scenarios to try to make all this concrete.
And we're also raising the level of excitement about PowerPoint.
Yes, because Clemens is a guy dealing with PowerPoint 2007 and a tablet. And so he has done these beautiful graphics, which we're unveiling for the first time today. And since he is living in the United States, he is politically correct. So if you count over the whole talk, you will see an equal number of male and female characters, outnumbered only by the endogenous people that make up the masses of database users in a few slots.
Right.
Okay. So the simplest database in the world, the simplest data an app can deal with, is data which is just owned by a specific user. Back in the day, that was pretty much the normal kind of data. Now we never think about it. But it is a beautiful and common scenario, a beautiful and common situation when you're just dealing with some data, right? Like my application is manipulating my data. I'm in PowerPoint and I'm writing a PowerPoint presentation. And unless I'm using Groove, I'm the only person editing this. And so I have a one-to-one relationship with my data. And you're going to find that there isn't a lot of architectural complexity in this situation. You just say, okay, I've got some data in my app, I'm acting on it, and most of the thinking that goes into this pattern involves the algorithms that are necessary to set that data up so that it's best accessed by the application. Whatever indexing strategy or structure you're going to use, what format you want to keep, you care more about interchange or locality and efficiency. So this is a pattern, though, and we kind of forget about these patterns once they get, nailed. The other kind of pattern we think a lot about is a shared database. And a shared database, I'm sitting here working away on the data, And then there's an arbitrary number of other people, but not a lot, just a small number of other people who are also accessing it. This might be a situation where I'm checking people out at the grocery store, and there are 5 other people also checking people out, and the work I'm doing is updating the computer's understanding of the inventory at the grocery store, that kind of thing. The key things here are to deal with locks, to deal with synchronization. At this point, I typically don't organize my data any longer with an eye towards the specific app's use, although I'll worry a lot about schemas. But I start to worry more about mediating access, making sure that if I'm accessing it and someone else is accessing it, we're not overriding each other, we're not getting in each other's way. And so this is an extreme thing where instead of there being 1 user, the moment there become 2, I hop over into the space where I have to deal with n people. And as long as there's not too many, so we start stumbling over each other, this is a manageable pattern that we've known for years. SQL is really nicely set up. And so what I'm still talking about here is a bunch of people hitting directly to the database. It turns out that there's an intermediate value to this, and here the graphic artist has gotten carried away with those squiggly lines. I must admit that I had an untoward first thought, but that's just people using the data, right, Clemens? That's access?
Yeah, they're all writing, but they're small work groups, so it's private to them.
So the fact that those squiggly lines are near the privates?
No, it has nothing to do with it.
Okay.
That's just your dirty way of looking at pictures.
Okay.
You're interpreting too much.
Clemens, I apologize for interpreting
I don't want to
too
know
much.
what's going on in your mind all the time.
Okay, I won't share what's going on in my mind with you anymore, only with the rest of them. How's that? So there's an intermediate place between a world where the database is public, and from the point of view of your app, kind of random people can come in doing other things, which is the second pattern, and a database which is owned completely by a work group, which will be accessed only by a small number of people using a particular app. And so you see on the one hand, there's the this is just mine. On the other extreme, there's a I'm using this, but who knows who else is dealing with it. Many different apps and so on. And then there's an intermediate place where I may be using the data and others are using it, but we all kind of know that we're using it under one application's guidance. Now this turns out to be a problematic stance. The reason I put the second thing first, even though it's extreme, is the moment that you start designing this to be used by a private group of people, you know some other app is going to be designed in 6 months that's going to start accessing it and you're in trouble. But these 3 examples kind of make the point that I alluded to at the beginning that I want to start driving home. It turns out that the decision as to whether you think of the world as here's a database that only I'm using, or here's a database that only I and my work group is using with one app, or here's a database that a bunch of us are using, but still a small number. It turns out that's not a fact of the world, especially if you step back and think about what's going to be happening over time. These ideas are not qualities of the world, although as architects we always think about it. How is this data going to be? It's going to be privately accessed. It's going to be used by many people. These are always design decisions that we use to parameterize the development effort. We say, we're going to decide to build an app that treats its data in one of these ways. In fact, there's no black and white. There's no time constancy. It's a design decision. And yet you count the number of times you hear people going through design discussions and they actually say, okay, we're going to treat this as a private database. Instead, someone studies for 6 months and tells you, oh, it's a private database. And it's really important to start thinking about these things as decisions you make when you're designing an app, because it's both responsible on your part to realize that's the idea you're creating, and it's kind of liberating. Because now you know, okay, in fact, I'm going to build an app like this. I know it's a lot easier to build an app where only one person does it. I'm in a hurry. I don't have to worry about random access. But I'm going to write it on the spec. The moment some second person comes and writes a new app that accesses this data, you're going to have to rethink the data design right here. So we want to start thinking about data characteristics as things in the head of the architect, not things out in the real world. A second kind of quality like this that we like to claim is a part of the reality, but is in fact a thing in the head of the architect, is read-only versus read-write. There's a kind of idea in the world that out there is a bunch of reference data, and it never changes. And thousands of people can go and access it because it's read-only. Now, I don't know of any data that has never changed. You know, it's a teleological point. You know, at the beginning, there was the Big Bang, and all the data has occurred for the first time at some point since then. But Wikipedia changes all the time. The book offering at the local bookstore changes all the time. Everything changes. Nonetheless, we often write applications that adopt this quality, that say, from the point of view of the access pattern, I'm going to count on this data being read-only. And the reason you do that is that if you can go look at a reference database, a dictionary, and you know it's not changing, you're able to make pretty broad queries over that data and count on the fact you're not going to trip over a lock. You can read it over a period of a half hour in pieces and count on the fact that you have a consistent view. So it's really useful in a whole variety of reporting and analysis and preparation for putting in a purchase order, all those kind of things, to be able to treat data as read-only.
And probably to enforce a policy that sort of makes it read-only.
That's true. So Clemens' point, which is really important, is that one of the things that you think about, once you make these assumptions, not only do you want to write them in the spec, but it's really useful to build them into the software. So when I'm back saying, this is a departmental database and it's only accessed from that app, if you have the means, you want to make sure that that app is the only one that can actually touch that database. Lock it down. So that the system itself can enforce these rules. Just so, you want to make sure that if you're going to write an app that assumes you're dealing with read-only data, that simplifies the business of writing the app, and it also should be built into the access pattern so that if the data does change, some error happens, so as everyone using the app can respond. Throw away all your work. The dictionary just changed. The smart guys in Oxford have added 50 new English words. Start over. You know, I keep pointing this at you, and you never change. You know, I could click this, and you would become the next Clemens. You could get really old by the end of this. It's enough.
Okay.
So the other extreme of read-only data is the assumption that you have what we call fresh data. Okay, read-only data is sitting there, and it never changes, and you're making the assumption. Another assumption you can build into the app is that whenever you look in that database, you have the exact true data. It's always correct. Now, in the same way as there's no such thing as read-only data, because it all happened and is likely to change someday, just so I'm going to argue there's no such thing as truly read-write, always fresh data. You know, I have a little gadget on Vista that tells me the weather back home. And I bet that weather is not actually the exact temperature outside the door of my house right now, even though it looks read-write. It's impossible to maintain data that is always accurate on a disk measuring the world because the world is always changing a little bit. It is possible, given a relatively slow-changing world and a relatively high access measuring system, to have data which is arguably read-write from the point of view of your app. But notice again, we've flipped from the objective notion of read-write to the subjective one. When you look at your app, you may say, I can maintain this database at low cost in such a way that you can treat it like it's read-write and treat it like it's fresh, and it always will be. But again, there's this notion, there is no such thing as read-only, and there's no such thing as read-write. There's no such thing as always never changing, and there's no such thing as always fresh. But nonetheless, you got to decide those things when you build an app. And so it's always a matter of deciding which of these assumptions you're going to build into your logic. Now, there's an intermediate story here where the data is neither treated as read-only nor as completely fresh. but rather where you make an assumption where the application is going to be built based on the knowledge that the data is always somewhat stale, but you know how much it's going to be stale. And what that means is that given your knowledge of that data source, that I know that data is always going to be good for 12 hours. You can read a copy down to a cache and work with it locally, and you can build knowledge of the staleness into your local application. And so in actuality, this is the only pattern we have. The dictionary has got a clock that says it's going to get stale every 20 years when the smart guys add new words. The temperature says it's going to get stale immediately if you care, except you know the temperature never changes by more than a few degrees. But what you really have in the world is this notion where you have an idea in your head of how quickly data changes, and you have an idea in your head of how much you care, and you can use those to come up with a model like this, where you make a decision about staleness and caching that's appropriate for your app.
And freshness and staleness is really only in the eye of the beholder. If we look at the perspective that any of those guys here may have on the data, depending on where you are in the business, if you have your CFO and he wants to see what the business does on any given day, they can say, I want to have a report about my financials as accurate. But does the CFO really care about the paper still being warm, the numbers being of a minute ago? It's likely that the CFO will not look at the report while the paper is still warm, but probably some hours later. So it's the freshness or staleness is always relative to who's looking at that data. There are environments in which scientific environments, or you could say financial markets, where data needs to be very accurate and very fresh. So if you want to have if you design a system that controls a manufacturing process, you certainly want to have very fresh data that you're looking at. If you are in a financial trading environment, you certainly want to have very fresh, most recent data that you're looking at. But once you get into reporting, or once you get into a place where people just don't care all that much about the accurate data, things change. So we can look at weather readings as something which must be very precise and very timely if you are if you're in some science institute. But at the same time, the same readings don't need to be as accurate and don't need to be as timely if you're just someone who's a consumer looking at some web page. So it's always relative to the use case, relative to the user of that data, of how you want to look at the data, of how you want to look at the information that's accumulated on the back end. So it's relevant for each of your use cases to look really at what does the consumer think about the data, and then make decisions about how you're using data, how you're replicating data, how you're doing all those things based on that perspective.
So the architectural trade-off here is if you think about the various scenarios, and Clemens is going to talk about some of them, you're going to spend more money in terms of your architectural time, in terms of your development time, and in terms of the hardware infrastructure to build a more timely database. And so you got to decide based on the use case how much work there is useful. And my observation in practice is people always make data too timely. And so there's just a little bit of watching a lot of people come and complain about how expensive it is to build systems that they don't in fact need. So we've talked about the use case, and we've talked about the problem of fresh versus non-fresh. The third problem we have is when data becomes really big. And so the fancy here is a huge database which needs so many computers to run that you have to build it by the dam so that you have enough power to run your system. Now, there's a guy named Jim Gray who...
We could also build it by a nuclear plant, but we want to be eco-friendly.
Well, and I live in the Pacific Northwest where we got things just like that. In fact, that looks like the dam right over the mountains from our house.
It's actually the Hoover Dam.
Oh, well, they probably all look kind of the same. Big concrete, water behind, dry space. Excuse me, Clemens.
That's okay.
So anyways...
I'm going to be driving over this in 2 weeks.
Yes. Clemens is about to have a baby, and his wife wants to go to Las Vegas for some reason before she has the baby. I don't even want to think about it. Anyways, so here we have a huge database, and there's a guy who we work with at Microsoft named Jim Gray. And one day I was talking with him about the design of these large databases, because he's made that kind of a hobby over the last few years. And he had an interesting observation. The problem with dealing with a large database is that it's really hard to avoid baking assumptions about locality into your data. So for instance, you're going to make an assumption somewhere in your design that you can run a query over a table, and it's all in one place. At the moment that database gets big enough that it can't fit any longer in one SQL system, you're doomed in the way of that architecture. And so Jim Gray suggests that when you begin doing your database design, you assume that there is a different database for each record. And you can then optimize the system once your architecture is done.
Can you repeat that once more?
Okay. You make an assumption that you have a different database for each record in your system. And you build your design on top of that assumption. And then he laughs and says, you then optimize for a world where you can put 2 records in the same database, and so on. But by doing that, you start with the assumption that you're going to be dealing with a big database. You build that into all your thinking. And that turns out to be a very useful assumption to make in these cases. Don't build in assumption. It's like building an assumption that your app is going to run on one machine and then trying to distribute it. If you start with an assumption that every module in your system is a service, you can then optimize it by pulling a few back on machine. But it's very hard to take an app designed to be in one processor on one machine and push it out to be distributed. But the data equivalent of that here in the big system is to make sure that you're not making assumptions about locality in your database algorithms at the beginning.
There's also, again, this is an architecture decision which requires moderation. So you shouldn't be building all systems like this. So let's assume this would be a customer database. And let's take 2 examples. Let's say you are a big maker of commercial airplanes. And this is your customer store, right?
You don't think the customer store of Boeing or Airbus is going to be so big that they need multiple SQL tables?
Well, you know, the records, they probably have 5,000 or 15,000 customers.
So here's the problem where you get a brand new architectural idea and then some sourpuss tells you it's not always useful. So it's true. Every time you don't need to think about putting your database next to a dam, you want to be humble about your design. And of course, this is the other side of all the advice we give you about always doing service orientation. In reality, you only need to architect enough. You don't need to architect to any ideal. But we are saying that you are going to run into situations where you need a big database. And so this is a quality of data. Like any other, it's an assumption you make, and you want to have it right. You want to make an assumption that's useful for your local use cases. But when you get in this situation, you need to think about this rule of Jim Gray's and not build in location assumptions. You heard the scream. The second problem you end up with, besides large size, is widely distributed data. This is the reality that when you're building an application in the real world, it's very rarely true that all the data you need is fresh and new and is going to be living in that app's database. In fact, new applications are almost always going to have to deal with data in several different databases across the system. When Don Box invented the tenets of service orientation, he was actually talking about service orientation as a quality of a module in a service-oriented application. We were thinking of service orientation as a module thing where those modules fit into a service-oriented architecture. Unfortunately, people picked up those tenets and tried to apply them to architecture. And the hardest one that they picked up was the one of autonomy. And somehow they meant that said that data could only live in one database. So we would get these complaints from people in faraway places who would come and say, I just read Don Box's tenets, and so I can't have that data live in 2 disks. And so my application reads data from 8 databases into one giant in-memory data set, and the queries are too slow. And I would say, you should blame Don Box for that. It's exactly what he was thinking.
The interesting thing about distributed data is that it's not always technically motivated, but there may be other motivations to have it and that force you to have it. So if we make this, again, customer databases, and we think about data protection laws as they exist around here in the EU, it turns out you cannot keep personal information about EU customers anywhere but in the EU or in so-called safe data havens. So if you're building an international, a global scope system, you will be ending up either hosting all the data you have in a data center in the EU, barring there's no law from somewhere else that forbids you to do that. So all of a sudden you end up with 3, 4, 5 data centers which all hold your customer data, but because of the privacy rules, you must distribute that data by law onto those data centers. So even though you have the goal of having one unified customer store, laws may prevent you from doing so. So you need to have a data access strategy and data distribution strategy which actually helps you with that, and those patterns help you with it.
Thank you for giving me a moment to get some water, Clemens.
Oh, I live to serve you.
No, I live to serve you, Clemens.
That's okay.
So the point is, in the same way that you may need to think about the size of your database from the beginning and architect in guarding against the assumption that all your data is in one data plate, in one big data file, just so in the world of distributed data, you're going to have to adapt a pattern if you believe your data is in several databases that takes that seriously. And we'll talk about the patterns for that in a little bit. But again, this is an assumption. You have to decide that at the beginning of your design, that this is going to be the way you build your app. Of course, this gets even worse when your data is scattered of different types in different places. So we have situations where I'm not just dealing with my customer data scattered hither and yon, but I'm in a world, say, of identity where I've got identity data in the SAP system, identity data in the Siebel system, identity data in Active Directory. Or I've got different kind of data all together in different places, and I've got to pull it all into the place where the app is using it. So this is sort of the even larger problem of the distributed data, where instead of having customers in different countries, I've got the customer data over here and the order data over here, and one of them is in Oracle and one of them is in SQL, and I've got to pull them all together.
And millions and millions and millions of euros have been sunk into misunderstanding the CEO who says, I want to have a single customer database. Right, and then people start integrating and start killing their apps and go and take their apps and just point them to a single place, and then they find out it doesn't scale. While the CEO really means, I want to have a unified view over my customer database. So the goal here is to just recognize the fact, which is never going to go away, that you have distributed data, different types of distributed data all over the place because they sit in appropriate places where they're being worked on. And if you want the projection of all that data, consolidation of all that data, well, then you need to create a unified view over them, but the goal is not to just throw them all into that huge database that needs to be powered by the Hoover Dam.
And so what we find out here is one of the levels of humility that our team has come to these days is built around how we understand the word federation. In the old days, we used to say, put all your data in one SQL place, or run all your systems in COM+, or build all your apps as N-tier, or whatever. In reality, we believe the architect's job today is to accept the fact that there is a diverse environment. And rather than trying to take all this data and move it into one place, running a 5-year war with all the other groups in your company, you build an architecture that can deal with the fact that this data is in other places and use the right patterns to accept that and deal with it gracefully and efficiently. Of course, this problem gets even worse if all this different data is in fact located all over the world. If you have, it's easy to use Active Directory in some sense to coordinate your identity data. Clemens can tell you stories of how easy it was for him when his identity was first established at Microsoft in Germany, but then he came to Redmond, and of course all the changes instantly, from the point of view of UCare, were spread across. But if you're in a world with diverse data sources scattered across the world, you're dealing with the hardest problem. It's important to pick patterns that are appropriate.
And of course, there are stories involved in here which have to do with bandwidth, with latency, throughput concerns. All of a sudden, all the problems that you have about just dealing with the data in distributed places just go bigger and grow bigger and bigger and bigger just because you have those additional constraints of the world being a pretty big place.
So we've talked about three qualities of data. Is it just mine? Is it shared by my work group? Is it open to everyone in the world? Is it read-only? Is it instantly read-write and completely fresh? Or more likely, is it some trade-off between the two? And is it a small, lovely database that will fit in Access? Or is it huge? Is it physically separate? Is it actually in many different technologies? And are you actually, unfortunately, going to have to build assumptions about latency and bandwidth into your app? And so that's the general characteristics of data. And like I said, what you need to do at the beginning of a design process, at least in my experience, is just write them down, take responsibility for them. It's not science, it's an assumption. And so your wisdom is involved with picking the right assumption, deciding what kind of data you're building, and then going ahead and using the right pattern. Now, the simplest pattern here, which you get to use if you assume that it's only one person and they're dealing with fresh data because they're the only one changing it, is to hook yourself up a local database and have at it. That's an assumption that most of the office systems make. You know, I've got my PowerPoint slide. It's an assumption you make when you have a little look-aside access table beside a database you're dealing with. You know, I run my family's annual pool for the bowl games in college football, and I just need a little database like this beside my Excel spreadsheet to store that data. This is a happy, lovely thing, and I unfortunately bet that none of you who are architects will ever be paid to design this system. Remote access is something that is an example of something Clemens was making earlier. This is often, in fact, a perfectly reasonable pattern when you're dealing with a small use where you're going to have a couple dozen people using a database. Just stand up the database, look at the average number of users at any moment in time and the number of database connections your database supports, and you may be able to do a two-tier system where the clients are just accessing the data, locks are sufficient to handle concurrency problems. When this is useful, it's an incredibly simple thing. The technology has solved this problem. And so if it's appropriate, it's a good pattern to keep in mind.
This is the click stop for, this is client server. The classic client server case.
Indeed, Clemens.
I just wanted to point that out.
Thank you, Clemens. I'm sure this talk is richer for you pointing that out.
Thank you very much.
I appreciate it. Can we have a round of applause for Clemens pointing this out? Now, what happens is that in almost all cases, you're going to have to be a little trickier as an architect when you're dealing with apps. So we used to talk about this mostly as handling the problems of the number of database connections or handling problems of locks. But there's a whole variety of things involving data transformation, concurrent access, non-standard error handling patterns, where what you want to be able to do is stick an intermediary between the database and the users. It's a it provides web-oriented or service-oriented access to databases that don't have the kind of things you need. It provides the ability to do high bandwidth work against the database, closer to the database if your clients are far apart. But the pattern is to say, rather than talking to the database directly, you talk to an intermediary. I think this is the click stop Clemens called
N-tier.
3-tier. We only got one up there, but N-tier, where you got intermediaries between the clients and the database.
And I often get asked, why would you put a piece of code in front of the database? Well, it turns out it's a pattern use, and it's not just because there's a gratuitous piece of code in front of it, but it's really about lowering the bandwidth that actually goes out. It's about being able to post-process data that comes out of the database.
We don't have yet in the company a consensus with everyone you'll talk about the trade-off between putting code in the database and having code outside the database. As a guy whose job it is to work on the team that puts code outside the database, the trade-off is very clear to me. And the way I think of it is, when you put code in a database, it better work. And you got those old gray-haired people who are my compatriots but have been working on writing stored procedures since they were 9, and they're really careful people, and they never make mistakes, and they never use up extra memory. And that code needs to be in the database because it's fast and you're ensuring access rules and ensuring checks and so on. Whereas if you got lazy guys like me in architecture who don't code so often anymore, the last thing you want is my code in the database. And so do you want an HTTP thread to enter that haven of security and then get hung because the browser went away? No. So there's all sort of reasons why you want the real safe solid code to be running, the infrastructure code to be running in the database. And there's equally reasons where the more error-prone or user-oriented code, the more often the code you have to change more often running outside the database. So that's how I think about it.
But there's also perspective that you can say the database per se, that's the tables and the indexes that you have. And the intermediary that sits in front of them is the stored procedure. So instead of actually going into the details, going into the assembly language of databases and actually dealing with the physical schema, you just create an abstraction in front of the schemas and the indexes and that reality, and just project out a very simple programming model for your data, which is a set of stored procedures, which creates an additional level of flexibility towards your concrete table. So you can actually change the tables, you can change data types, you can go and change your query strategy without really subjecting your application to any of those risks of those changes. So even if you are doing a database-centric architecture in that way, using stored procedures as the only way to go and approach the database is giving you an additional level of loose coupling.
So broadly, we have three choices here, though. Either we got a database that we're accessing ourselves, we got a database we're sharing, or we got a database that's being accessed via an intermediary. Those are the basic access patterns of databases. Like I said, it's pretty clear when you use which one. You use the simplest one you can, but often you need to use the more complex one, which is right here. Now let's deal with a common problem. Your architecture is often going to be determined based on the error handling strategy you have. And again, we have three error handling strategies, going from the most simple to build to the most complex. If you can afford the coupling and lock behavior of ACID error transactions, they are a great strategy to use to guarantee consistency among state changes out in the tables. And so in the same way as it's sometimes possible to just use a database without an intermediary, just so it's often possible to just use a database through ACID. What happens is when you walk in, you're put in the right order, you're accessing the data, and everything is relatively straightforward because the infrastructure can deal with it. The great innovation of MTS and COM+ is to make these kind of applications really easy to write. And so this is a real useful strategy to deal with potential errors in applications to turn on two-phase commit and ACID transactions. But sometimes that's really expensive. And in fact, if you look at any scalable application that we all use, you very rarely get into a situation where that's happening. I don't see two-phase commit at the airline. Instead, they use a strategy like this. They let all the access go through their intermediary to their database, and they make a list of all the people who are in trouble. And that list gets given to somebody someday, blah, 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 there's some problem. And the client encounters the human process at the airport. Who would like to take $300 to fly 6 hours from now? This turns out to be a very standard strategy for dealing with errors, is to make a list of them, to not lock data access, but rather to build your application so as the application can keep a list of trouble, and then print out a list of the trouble spots and have some person deal with it.
So you can imagine this here, really this log being an email sent to a call center agent who then picks up the phone, calls the customer, and apologizes on your behalf and tries to fix it.
And the thing is that compensation logic is tricky to write. Humans are real good at that sort of thing, at figuring those kind of problems out. So this is a very common strategy. Increasingly, though, we see people dealing with the third problem, where the list that comes out of errors is actually machine readable. It's in a log. And the business of writing an application involves writing the logic in the intermediary, keeping track of problems, and writing a second application that fixes up the problems. You know, the application may send a mail saying, I'm going to get that for you and it's going to be ready in a week. Puts in the order. When the order comes in, you then finish. It may be someday an airline will actually rebook you, and so on. It's automating the response to that error log. And this is an area where we believe there's a lot of work we can do in the coming years to improve the programming experience. Right now, we make it real easy to build two-phase commit. We make it real easy to build the intermediary. But it's not so easy to build compensation into your application in a simple way. Especially as we move towards more decoupled service-oriented architectures that are event-driven. We need a strategy that decouples error handling as well as it decouples logic. And so where you'll see us move is towards these, excuse me, Clemens, where you'll see us move is in these directions of trying to make it easier for you to architect and build compensation into your system.
So one of the, for those who saw the big Visio thing yesterday, one of the things to realize, and that's what we have started to realize when we were looking at those things, is that the paths that the errors go in a system are just as important as the sunshine architecture that you have when you look at how the system shall work. It turns out that if you have something, you have a distributed system, you have 25 services cooperating, and some services starts failing, the path which the errors go are not necessarily the same communication paths. It's especially interesting when you consider that some of those paths that you go in are one way, right? You have a queue going from here to there. What do you do if one of those services starts failing? And what are the consequences for the business process overall? Very often you can deal with the technical errors much easier than with the consequences of you're not being able to ship an ordered product to a customer. How do you deal with those situations? These failures have business impact, and you need to address this in explicit error design in your application.
So we've talked about the patterns we use for access. We've talked about the patterns we use for errors. There's a third sort of situations we were talking about, which is the patterns we use for distribution. And the simplest pattern that we use for distribution is to try to get data out of the main store where it's subject to changes, subject to lock issues, and move it into a secondary cache where it can then be accessed by the application. Now, remember how we talked about the fact that you can make assumptions in each data store about the timeliness of data. And you can make assumptions about the freshness of data and the read-only versus read-writeness of it. It turns out that you can build applications that transform, the way I think about caching, and the next pattern I'm going to tell you, as a transformation from one set of those assumptions to another. I have data over in that store that is incredibly fresh, but I'm locking it all the time to keep it fresh. To keep most of my readers from tripping over those locks, I'm going to translate that data into another store that's only going to be timely up to a half hour, but they have complete access to themselves. And so now what I do is I change the assumption I'm making about the original app. I add this caching transform. And now instead of dealing with a real live database, which I may need live for some other purpose, I deal with a slightly stale database. And I can make that transform any way I like. And so if I see, remember at the beginning when I was talking about the qualities of data, I kind of skipped the assumption that, in fact, different parts of the app that are going to access data, that they may have different needs. So the story here is I can always transform data to being more stale pretty easily. And if the particular part of my app that's doing access needs that, then this caching pattern is great.
And what you can do to actually help making decisions about that data that you hold here, that you access, is there's a lot of information that's sort of there, which exists over in the shared database about when that data gets updated or how high the risk is that the data gets updated. If the shared data here is a sales catalog, you can be pretty sure that that sales catalog is not going to be updated every minute, but there's a publishing cycle, and your prices will change, if at all, only every 24 hours, or probably only every week. You can take that information, knowledge that you have about the timeliness of the data, the requirements, and you can encode that into the flow of data as it goes into the cache. You can send out-of-band information. You can say, the next update of that data is going to happen tomorrow at 12. All of a sudden, it's very easy to manage those things. There's a lot of information sitting at the source of the data that you can send around to the caches and just let the application, the local application, make decisions about the reacquisition of the data, to make decisions about whether to display a warning. You know, all those things can flow as out-of-band additional information with your data.
So in the same way that we can use the caching pattern to deal with differences in the requirements for the timeliness and freshness of data, different of the data characteristics, just so we use this pattern, which I'm calling federation, to deal with differences in the location of data. Remember I talked about the qualities of data being its freshness and then its location. So suppose I have multiple fresh databases with some view, but my application needs some different view, and it needs to be a relatively timely view. I'm going to be doing a lot of edits, but it's a view that doesn't exist in any data in the world. This is the pattern that we send back to our friends who are trying to read things in a big data set. And what you do is you add a layer in front of your databases. And your layer is it's pulling the data you need out of the back-end databases and loading it into a table particular to this application. And then what you want to do is provide a full set of the CRUD operations on this local view. You're going to find that add is not so tricky. The odds of getting a conflict in adds are pretty small. Get is not so tricky. That just refreshes by pulling all the data from the back. Delete is not so tricky. A little more often conflicts, but not great. The trick, of course, is update. I've pulled all this data from my stores that are all over the world or all over the continent or in different departments into my app store. I've updated it, and then I want to push it out. What happens is that you can solve the problems of concurrency there with locking, but you typically don't want to. Instead, what you do is you build a workflow there. And what that workflow does is it looks at the updates are needed. It looks at any place where the data has changed. So typically, this system keeps a last view of the data it pulls in. So it has an in-memory view of all the systems it's dealing with. When it goes to do its push out during an update, it gets another view. It looks at all the deltas. And then it has logic. It says, OK, if my local user has changed this field, they actually know what they're doing, so I'm going to go override the update out there. Or my local user doesn't know what they're doing, so I'm going to postpone distributing some of these updates and send an alert back to the client. It turns out that once you start building these things, you're going to find that that update logic is a part of your app. There's no consistent, simple way of building it. But what you do is you build your data view, and then you deal with the timeliness of your updates. And you go ahead and write the logic as part of the app that says, OK, what happens when I'm editing this data and it's changed elsewhere? And it turns out that that's app-specific. So the answer to the question, what do I do if there's data scattered hither and yon, and I want to bring it together to build an application? What I do is use this federation pattern. I hook up a connection to all the databases I care about. I hook up a general system to pull the data in on gets, push it out on updates. And I directly implement business process to deal with situations where the updates are in conflict. It's a very common pattern. It's not very hard to write. Once you build it once, you have infrastructure that you can use again and again, just changing the work process. So it's a very easy to, easy isn't right. It's a straightforward pattern that doesn't require a lot of work as you implement it over and over. That's, of course, the key that say someday we're going to want to give this to you, so you don't have to build it again and again. Sell this to you. Excuse me, marketing guys. The third pattern we use in the world of big databases is replication. So in the world of federation, that's mostly necessary when I'm doing updates. If I'm in a situation where I have assumed my data is read-only, then I'm in a great situation to replicate the data. And so I build an infrastructure that whatever the requirement is for this data, I can push it out into multiple places, to distribute it geographically. When you go online to a big web store, you can bet that the data you're seeing is replicated hundreds of times so they can scale. And every web store in the world will tell you, I've got somewhere between 3 and 16 Camaros on the lot. Please order the one you want, and I'll hope to be able to serve you. So this replicated data has its own assumptions about its timeliness, rather than being apologetic about it, since they know they need to scale by doing this replication. They just build the lack of timeliness, the staleness of the data into the app. Again, that's what I meant earlier when I said these qualities are your assumption. They're not in the world. We obviously don't need timely data from our scalable web stores because we never get it and we still use the stores. Many of your apps where you need to scale out, since you can't scale out real-time data and no one seems to need it, don't worry about it. Do replication and then build the app in with this knowledge. The final situation here is read-write replication. Read-write replication is relatively straightforward to do in a world where there's not a lot of concurrency, but you can do it even with concurrency. And the way you scale out writable data, and by which I mean now I'm going to do updates, but I don't need to federate it, is I make copies of the data. Typically now, rather than scaling out by putting the data, the exact same copy of it on many machines, which I do in the read case, I scale out by splitting my writable data onto many machines. 1/10 of the bank accounts are here, 1/10 of the bank accounts are here, and so on. Hopefully, I'm the only person accessing my bank account, so there's not a lot of concurrency problems. And so the problem of this system is to have a router that sits in front of the data system, your intermediary. And what it does is it looks at the record you're accessing. Either you put those records in concurrent order on the tables in a range, which makes that hash key easy to write, or you have them scattered all over the place, which makes it hard. But you have a router that sends you to the appropriate database to get right access to the system. Sometimes the distribution is based on geography, like in the EU case where my customers need to live in their country of origin. Sometimes it's just part of my architecture where I want to have a big scalable system where I can put my data on many machines. So I can have a lot of auctions or sell a lot of different stuff on the store or have a lot of accounts. The difference here is that when I'm doing read-only replication, I almost always copy the data because my constraint there is just how much data can I put on a machine. Whereas when I'm doing read-write, my problem is contention for the data. And so I like to spread it out. My scale-out strategy involves getting to the right machine, and the number of accounts or records on the machine is based on the performance of that machine. Okay, so we're about to switch over now. Oops, sorry. One last thing in this scale-out story is, if I have my read-write data, what if I want to do read-only and read-write? This happens a lot where the boss says, I want you to give me an up-to-date report on the customer account data. And I've got a nice scalable system where the customer account data is scaled out on multiple machines with the router in front of it. And now I go and run a report across all those machines and trip over lock after lock after lock as I'm getting a copy. And so this is where the read-only and read-write come together. Never do a report on read-write data. The report is already going to be old when it's printed between the time it goes to the boss. Make a copy of all the data.
And the numbers won't add up.
There you go. Make a copy of all the data, put it in a nice system with almost fresh. Run your reporting on the copy. If you think of large scalable websites that do auctions or database or stores, the read-only access is done through a copy that's a little bit stale. The read-write access is done through the actual system. When you're searching for auctions, you don't get the last half hour's worth. When you're searching for books, you only see the books as they were 3 hours ago in the database. When you actually go to get your order in or put a bid in, you're going to the right database. So this is the most general combination because, of course, you can replicate that read-only data. So this pattern is the ultimate pattern for dealing with distribution, especially if you add the fact that these read-write tables might each be federated using that earlier pattern. So you use replication, copying to deal with read-only scale-out. You use routing and distribution to deal with read-write fade-out. And you use federation to deal with multiplicity in data stores. 3 characteristics of data: who's using it, its freshness, and its distribution. 3 kind of patterns: access patterns, these distribution patterns, and the error handling patterns. So in the first talk we had 1 group of 3 patterns. Here we have 2 groups of 3. 3 kinds of characteristics, 3 kinds of patterns. Now let's talk about scenarios.
Yep. Thank you, Steve.
You're welcome, Clemens.
All right. So we're going to put all those together. Let's start with Outlook Exchange, as we did in the last one when we talked about logic. Outlook and Exchange are always good examples. So your email inbox, your calendar, your contacts, your email drafts, and the outbox and your tasks are all private. These are yours. While the corporate address book is not yours, it's actually managed by someone else because it's replicated in from or synchronized with Active Directory. So that's the Human Resources Department that owns that. Public folders are also of that character. So you have private data that's only yours, and you have public data that's managed by others. That's reflected in the architecture of Outlook and Exchange. Then you have data that's stable, that will never change, such as your email inbox will never change unless you get new email.
Or delete email.
Or delete email, but these are explicit tasks. But as long as you don't replicate, that's fine. If you replicate, if you don't replicate, if you haven't replicated with the Exchange server for a while, or you have not downloaded mail, you may be looking at a stale projection of the mail that's actually there for you. If you have replicated and you're connected to Exchange server, you look at a fresher copy. Your email drafts are, and the outbox is read-write. You write to it. The inbox is, of course, read-only, right? And it's always fresh because that's your personal view. There's outside knowledge about your mailbox if you're connected to Exchange, because there may be something in the queue for you that you don't know about. But stuff you produce yourself is always in your view. So you have always a fresh view. So you can look at, again, you can look at all those different characteristics very easily by looking at Outlook and just reason about what's in that folder and how does it work. So again, Outlook is a good exercise to look at. Let's look at some other versions or some other applications of those things. One of the databases, very volatile databases, but still we want to look at this as a database, just mostly because we want to make you thinking about databases in a very broad way. It's just a data store, it doesn't need to be SQL, is a game. So I have 4 people connected through System Link or through Xbox Live playing Halo. There's a huge amount of data that all of those people are sharing, and there's little contention. They're all writing. It's all read-write, and it's got to be always fresh because you need to know where the next guy is who's just shooting at you. So that's a data distribution story. And they have huge issues about timeliness, about bandwidth constraints, but it is a data store. There's some common knowledge that's accumulating. Now, the interesting thing here in the Halo example or any peer-to-peer gaming experience is that you have the common data store is just a projection that's shared. So actually, those databases don't reside somewhere in the middle, but they actually reside in the mesh. Everybody knows about those things. If someone rejoins a peer-to-peer experience, they just go and get a replica of all the data that's out there in the mesh and just build a local view of it. So it's even if you're looking at a system like this, the reality of it is that you may actually have something that's not sitting in a local store, but that may be just common knowledge inside a mesh of peers. So the database is just an illusion. The data store is just an illusion. The bank machine is a very interesting application of the pattern with an intermediary. Because the bank machine goes to the intermediary, which is the bank that owns the ATM. But then it actually goes out through the master system or whatever other system, and actually goes and checks your bank account, your bank, whether the bank is willing to give you the money. So you have an intermediary sitting in front of a number of databases, a number of systems connected to that worldwide network, and they will go and check your account whether you're actually good for that money. It used to work in earlier times with just a blanket guarantee that the bank would give you, and they would say, you are always good for that amount of money because you have our card. So they would make that as guarantee. Now that systems are more connected, they actually can go and check that account in real time, and that's what they do. But it's every ATM or the backend system behind the ATM acts as an intermediary service that then goes out to the respective systems and the data stores where your account sits and actually goes and asks them.
It's interesting to compare this problem of accessing a bank account with a different problem, say, of a McDonald's trying to put an order in for all the buns they need in their store the next day. Here, pretty much 1-for-1 or 2-for-1, users each map to their own record. And so you can count on there being very little contention on the records in that use case. Whereas in McDonald's, everybody's trying to buy the buns or get the buns from the same store. And so broadly speaking, everyone is accessing the same store. And what you'll see in those systems is the bank machine is willing to give you the illusion of request response and immediate timeliness because they don't need to worry about contention when they scale. Whereas the store purchase problem, they will never give the store owner, I promise you you're going to get 5 things of buns. They'll just say, I know you're not going to get those buns, or maybe you'll get those buns. Because they can't hold a lock and scale. And so these patterns, as you look at them, they all exist because you can tie back to the qualities of data. You can treat a bank account as fresh data, and so you can give direct access to it. You can't treat a store as direct access, and so you have a different pattern. What you do is you make your assumption about the quality of the data, and then you build out the app access pattern accordingly.
So here's one of our favorite examples, because it illustrates the Jim Gray pattern quite nicely, and that's Hotmail. When you go to Hotmail or LiveMail, and you punch in your name and your password, you will find, if you look at the URL, you will end up at something like Bay 10 Blade 3. It's actually quite explicit in the URLs these days. It's actually saying Bay and then BLD, I believe, which says this is the rack and this is the blade, and that's where your Hotmail inbox sits. And most of you will see different numbers showing up for them, and that all depends on how long you have had your Hotmail account or your LiveMail account, and on what the load is on the respective systems. So Hotmail was built with this pattern of 1 record per machine, and then as an optimization strategy, they bucket you with 50,000 of your best friends, or whatever number, and you share a machine with them. So this is an implementation of the reporting pattern in some ways, and the read-write distribution pattern, and that you own this machine. You actually own a record on that machine. In the Hotmail reality, there's a service sitting right in front of that database, which has an HTTP front end. So what the Hotmail page will do, the landing page, is it's going to look you up, and it's going to do that with the index service. And then the index service knows where you're located, and it will then redirect you to the service that sits right on this machine. So the HTTP service, and this is where your access logic, this is where your Hotmail thing sits. So it's going to just redirect you to the place, and you can go and read-write on your own record as much as you want because nobody else is going to look at it. So there's clear ownership. This is limitless scale. They can just add machines as they get more users, because everybody's going to be redirected to their systems. Now, because Hotmail the usage pattern is very particular in that people sign up for Hotmail accounts and then just go and abandon them, they need to have something that goes and rearranges the mailboxes every once in a while, and that's the job of the load manager. So the load manager looks at the buckets and it starts rearranging those, which means it marks yours for moving to another machine. And then in the next run, it will actually go and move that account. And then it goes and updates the index, which is a read-only thing. And it's a private copy to be used by the redirector. And then the redirector is going to make decisions based on that. So we have an index sitting in front of n machines, and the redirector will point you to the right one, and you have read-write access to your own copy, and nobody else will look at it. If there were any reporting run on those stuff, so let's assume this was not Hotmail, but this was a trading scenario, an e-commerce scenario where these would all be customer profiles. Let's assume Amazon wants to know what people are currently looking at, what's a hot topic. They would go and just consolidate all the data that sits on all those machines in one warehouse. So we'll pull this data out and run reports over them on the warehouse.
So the pattern here goes, the pattern here is that for both the bank account and Hotmail, the first problem is to set up this redirector and scale out, read-write. It turns out we all use our bank accounts more or less equally frequently. You may make 20 withdrawals a month, I may make 40, but there are very few bank accounts that are not used at all and very few bank accounts that are used thousands. Whereas there's a huge variety in Hotmail in terms of the load. So once Hotmail does the first optimization, they're then forced to do a second one. And these patterns compose that way so that you can make assumptions about the data, discover problems, and then add solutions. The advantage of these patterns we're showing you is they all compose nicely. And so you can put them together as you need and are experiencing problems.
So here's a variety of this, which is Contoso auctions. You can figure out who that is. And so we have an auction database. Now the auction is interesting because the data is different. While a Hotmail inbox lives on for years and years and years, I have mine for I don't know how long. An auction has a finite time lifetime. You set up the auction, it's good for 10 days, it's furthermore retained for 3 weeks, and then it goes away. Means you don't need to have a load manager because you know those things will expire, and you can make predictions about the load you have, the data load you have in your systems. You know the total number of auctions you have at any given point in time, so you can go and scale out. But what you can do is, as you're allocating your new auctions, you simply go and encode the machine number straight into the ID of that auction. So whenever someone walks up to you and just requests the details for an auction, you simply look at the code, look at the ID, and says, all right, that sits actually on machine 01001, just redirect them there. So it's the same pattern as Hotmail, but just the strategy here depends on the longevity of the data of the record that you're actually dealing with. So again, that's another concern, but it's the same set of basic patterns. Here we have MIIS, the Microsoft Identity Integration Services, and they are concerned about the shared read-write.
The federation pattern.
The federation pattern, yes. So the federation pattern here is MIS tries to go and synchronize data between Active Directory and a whole lot of other systems. The truth in an enterprise environment is that you don't have one record where your username and your password and your information sits, but actually you have many, many, many places where that's maintained. So you have an HR system, which may be sitting in SAP, where all the personnel records are kept, and that's where your the data ends up that the HR department puts in. Then you have a self-service portion where you can go and just change your own address, so the HR department will learn about this, but that may actually be entered into Active Directory. Then you may be running Lotus Notes as your email system, and of course that needs to be provisioned because that has its completely own security notion. Then you have custom systems like a loan system and an insurance system which all have their own notion of identity. So what you need is a thing that goes and now provisions all those systems and actually takes the changes that you make in any of those systems and sets up rules for how those things are moved forward and backward. So this is the whole distributed update problem. How do you deal with those things? So let's say you have a self-service app, we call that HatTracks, inside of Microsoft, and if I change my address, I just go to HatTracks and just change that address right there. HatTracks will go and update Active Directory. This will trigger something. MIS is going to kick in, and MIS will then go and take that data and just replicate my data out, my personal new address, out into other systems. In case there's a conflict, which there will be, MIS has a set of rules which says this system is normative for this field, and this system is normative for this field. So MIS is all about building rules for replicating this, for federating this data, and even though we're all dealing with one record, one imagined record, which is never stored at any given point in time in one system, we have a negotiation infrastructure which sits in the middle and actually goes and has rules about replicating those things. And if it detects a conflict that it cannot resolve with a set of rules you're giving it, it will throw up an administrative alert, and then a person needs to deal with it.
It's a beautiful architecture. So if you were tempted when I described the federation pattern, and you realize that you might have reason to build that into your apps at home, while this is a special purpose system that only deals with identity, it's really useful to go get the white papers that describe its architecture and read them to see a way that you can build out a federated system yourself, because they do it in a very simple and straightforward way that's not difficult to project into custom code.
So here we have a sales statistics database, and that's all about pulling in all the information about how is your business doing. It would be not very wise to go to all of those places and try to do a live scan of what's going on and how the inventory looks, because that's going to give you a false view, because you can't query them all at the same time. You can't get you can't get the numbers to add up. So what you need to do is you need to get the system into a stable state, into a consistent state, and that's only something that the database can know. Then you create a snapshot of it, and then you feed that snapshot, you consolidate that snapshot into the common reporting warehouse, into a data warehouse, and there you have a stable, consistent state from all three places where you then can do and run your reports. And typically you don't want to run one report, but actually want to run multiple reports. You want to have different pivots on your data. If you do that on live data, you look at one pivot, and the second pivot you look at, well, that's already running on something else, on completely different data. So it's actually unhealthy from a business perspective to do any reporting on any live data. You must have a copy that will allow you to look at the same thing from different angles and not at different angles of something that's ever changing. Active Directory is giving you another pattern. That's also the read-write federation pattern. And that's about you not worrying too much about what you're talking to. You always talk to your local domain controller, and Active Directory actually does the magic behind the scenes to get the data from A to B. So it's taking care of distributing the data for you. So you can imagine if you think about Active Directory really as a data distribution strategy, if you need to have data read mostly data, which has very non-frequent updates, if you want to distribute that in your organization, Active Directory is actually a good strategy, a good infrastructure to replicate that, because it knows how to do this. It knows how to do this on a global scale. So using Active Directory as a data propagation tool is actually a good idea.
Clemens, what kind of company would work in big cities like Seattle and Kuala Lumpur, and then a little town I never heard of like Mönchengladbach?
See, that's just my local pride that bleeds into those slides.
But how can you expect anybody to know these little farm towns?
Oh, it says D.
What is D? How come there's only one letter?
We only have little farm towns.
In G, you mean?
In D.
D?
Yeah, D.
You got your own name for everything.
Deutschland.
Ah, all right. Seems ludicrous to me, but go ahead.
So I think what we're going to say here, or what we have said, is Not all data is equal. A common, I don't want to call it mistake, but maybe it is a mistake, is that you just look at data and you just think it's all good in the database and you just treat it all in the same way. I think what we've tried to illustrate and hopefully have succeeded in is to show you that you need to be looking at every single record, every single table in quotes, and think about what are the requirements, what are the patterns, what's the consumption expectation about the data, and how do we deal with those things? Not all data is equal, and it's not only a solution, to just leave it up to the database and not just slam it all into a single store and that's it. The key to optimizing any distributed systems architecture, the key to get things to be speedy and to have high throughput and actually to be robust is proper data architecture. You'll hear me and many other people speak up against dumbing down the data access. The reason for that is that we believe that data architecture is very, very important. So, just abstracting away your data access, just saying, it's all objects and they can be automatically persisted to the database, that's all fine, as long as you respect that data flow and data architecture is really important.
It's done, Clemens. No more philosophy. Go to the Iron Architecture, where you'll find competitions in things like the architectural hurdles. 20 problems in front of you, leap over all of them, touch none of them, get to the other end. Clemens and I have already spent some time down in the experts area. We will continue to do so this afternoon, probably after 3 or 4. We'll surely be down there Friday. And if you feed out feedback here, we'll make sure you get a chance to go to München Gladbach and see all of the sites.
Yeah, thank you.